Zero, the biography of a dangerous idea written by Charles Seife. Part 0. Null and void. Zero hit the USS Yorktown like a torpedo on September 21, 1997, while cruising off the coast of Virginia. The billion-dollar missile cruiser shattered to a halt. Yorktown was dead in the water. Warships are designed to withstand the strike of a torpedo or the blast of a mine. Though it was armored against weapons, nobody had thought to defend the Yorktown from zero. It was a grave mistake. The Yorktown's computers had just received new software that was controlling the engineers. Unfortunately, nobody had spotted the time bomb lurking in the code, a zero that engineers were supposed to remove while installing the software. But for one reason or another, the zero was overlooked and it stayed hidden in the code. Hidden, that is, until the software called it into memory and choked. When the Yorktown's computer system tried to divide by zero, 80,000 horsepower instantly became worthless. It took nearly 3 hours to attach emergency controls to the engineers, and the Yorktown then limped into port. Engineers spent 2 days getting rid of the zero, repairing the engines, and putting the Yorktown back into fighting trim. No other number can do such damage. Computer failure like the one that struck the Yorktown are just a faint shadow of the power of zero. Cultures girded themselves against zero, and philosophies crumbled under its influence. For zero is different from the other numbers. It provides a glimpse of the ineffable and the infinite. This is why it has been feared and hated and outlawed. This is the story of zero, from its birth in ancient time to its growth and nourishment in the East, its struggle for acceptance in Europe, its ascendance in the West, and its ever-present threat to modern physics. It is a story of the people who battled over the meaning of the mysterious number, the scholars and mystics, the scientists and clergymen who each tried to understand zero. It is a story of the Western world's attempts to shield itself unsuccessfully and sometimes violently from an Eastern idea, and it is a history of the paradoxes posed by an innocent-looking number, rattling even this century's brightest mind and threatening to unravel the whole framework of scientific thought. Zero is powerful because it is infinite. They are equal and opposite, yin and yang. They are equally paradoxical and troubling. The biggest question in science and religion are about nothingness and eternity, the void and the infinite, zero and infinity. The clashes over zero were the battles that shook the foundation of philosophy, of science, of mathematics, and of religion. Underneath every revolution lay a zero and an infinity. Zero was at the heart of the battle between East and West. Zero was at the center of the struggle between religion and science. Zero became the language of nature and the most important tool in mathematics and the most profound problems in physics. The dark core of a black hole and the brilliant flashes of Big Bang are struggles to defeat zero. Yet, through all its history, despite the rejection and the exile, zero has always defeated those who opposed it. Humanity could never force zero to fit its philosophies. Instead, zero shaped humanity's view of the universe and of God. Part 1. Nothing doing. According to Rigveda, there was neither non-existence nor existence then. There was neither the realm of space nor the sky, which is beyond what stirred were. The story of zero is an ancient one. Its roots stretch back to the dawn of mathematics in the time thousands of years before the first civilization, long before humans could read and write. But as natural as zero seems to us today, for ancient people zero was a foreign and frightening idea, an Eastern concept born in the Fertile Crescent a few centuries before the birth of Christ. Zero not only evoked images of a primal void, it also had dangerous mathematical properties. Within zero, there is a power to shatter the framework of logic. The beginnings of mathematical thought were found in the desire to count sheep and in the need to keep track of property and of the passage of time. None of these tasks required zero. Civilizations functioned perfectly well for millennia before its discovery. Indeed, zero was so abhorrent to some cultures that they chose to live without it. Part 2. Life without zero. It is difficult for a modern person to imagine a life without zero, just as it's hard to imagine life without the number 7 or the number 31. However, there was a time where there was no zero, just as there was no 7 and 31. It was before the beginning of history. So, paleontologists have had to piece together the tale of the birth of mathematics from bits of stone and bone. From these fragments, researchers discovered that Stone Age mathematicians were a bit more rugged than modern ones. Instead of blackboards, they used wools. A key clue to the nature of Stone Age mathematics was unearthed in the late 1930s when archaeologist Carl Absalom, sifting through Czechoslovakian dirt, uncovered a 30,000-year-old wolf bone with a series of notches curved into it. Nobody knows whether Gog the caveman had used the bone to count the deer he killed, the paintings he drew, or the days he had gone without a bath. But it is pretty clear that clearly humans were counting something. A wolf bone was the Stone Age equivalent of a supercomputer. Gog's ancestors couldn't even count up to 2, and they certainly did not need zero. In the very beginning of mathematics, it seems that people could only distinguish between one and many. A caveman owned one spearhead or many spearheads. He had eaten one crushed lizard or many crushed lizards. There was no way to express any quantities other than one and many. Over time, primitive languages evolved to distinguish between 1, 2 and many, and eventually 1, 2, 3, many, but didn't have terms for higher numbers. Some languages still have this shortcoming. The Siriona Indians of Bolivia and the Brazilian Yanova people don't have words for anything larger than 3. Instead, these two tribes use the words for many or much. Thanks to the very nature of numbers, they can be added together to create new ones. The number system didn't stop at 3. After a while, clever tribesmen began to string number words in a row to yield more numbers. The languages currently used by the Baccheri and the Bororo peoples of Brazil shows this process in action. They have number systems that go 1, 2, 2 and 1, 2 and 2, 2 and 2 and 1, and so forth. These people count by twos. Mathematicians call this binary system. Few people count by twos like the Baccheri and Bororo. The old wolf bone seems to be more typical of ancient counting systems. Gog's wolf bone had 55 little notches in it, arranged into groups of 5. There was a second notch after the first 25 marks. It looks suspiciously as if Gog was counting by fives and then tallied groups in notches of 5. This makes a lot of sense. It is a lot faster to tally the number of marks in groups than it is to count them one by one. Modern mathematicians would say that Gog, the wolf carver, used a 5-based or quinary counting system. But why 5? Deep down, it is an arbitrary decision. If Gog put his tallies in groups of 4 and counted in groups of 4 and 16, his number system would have worked just as well as would groups of 6 and 36. The groupings doesn't affect the number of marks on the bone. They only affect the way that Gog tallies them up in the end, and he will always get the same answer no matter how he count them. However, Gog preferred to count in groups of 5 rather than 4, and people all over the world shared Gog's preference. It was an action of nature that gave humans 5 fingers on each hand, and because of this accident, 5 seemed to be a favorite base system across many cultures. The early Greeks, for instance, used the word fiving to describe the process of tallying. In fact, knowing about numbers at all was quite an alibi in prehistoric times. Simply being able to count was considered a talent as mystical and arcane as casting spells and calling the gods by name. In the Egyptians' Book of the Dead, when a dead soul is challenged by Aken, the ferryman who conveys departed spirits across a river in the netherworld, Aken refuses to allow anyone aboard who does not know the number of his fingers. The soul must then recite a counting rhythm to tally his fingers, satisfying the ferryman. The Greek ferryman, on the other hand, wanted money, which was shoved under the dead person's tongue. Though counting abilities were rare in the ancient world, numbers and the fundamentals of counting always developed before writing and reading. When early civilization started pressing reeds to clay tablets, carving figures in stone and daubing ink on parchment and on papyrus, number system had already been well established. Transcribing the oral number system into written form was a simple task. People just needed to figure out a coding method whereby scribes could set the numbers down in a more permanent form. Some ancient societies even found a way to do this before they discovered writing. The illiterates Incas, for one, used the quipu, a string of colored knotted cords, to record calculations. The first scribes wrote down numbers in a way that matched their base system and predictably did it in the most concise way they could think of. Society had progressed since the time of Gog. Instead of making little groups of marks over and over, the scribes created symbols for each type of grouping. In a quinary system, a scribe might make a certain mark of 1, a different symbol for a group of 5, yet another mark for a group of 25, and so forth. The Egyptians did just that more than 5,000 years ago, before the time of the pyramid. The ancient Egyptians designed a system for transcribing their decimal system, where pictures stood for numbers. A single vertical mark represented a unit, while a heel bone represented ton. A swirly snare stood for 100, and so on. To write down a number with this scheme, all an Egyptian scribe had to do was record grouping of these symbols instead of having to write down 123 tick marks to denote the number 123. The scribe wrote 6 symbols, 1 snare, 2 heels, and 3 vertical marks. It was the typical way of doing mathematics in antiquity, and like most other civilizations, Egypt did not have or need a zero. Yet the ancient Egyptians were quite sophisticated mathematicians. They were master astronomers and timekeepers, which meant that they had to use advanced math thanks to the wandering nature of the calendar. Creating a stable calendar was a problem for most ancient peoples because they generally started out with a lunar calendar. The length of a month was the time between the successive full moons. It was natural choice. The waxing and waning of the moon in the heavens was here to overlook, and it offered a convenient way of marking periodic cycle of time. But the lunar month is between 29 and 30 days long. No matter how you arrange it, 12 lunar months only add up to about 554 days, roughly 11 short of the solar year's length. 13 lunar months yield roughly 19 days too many, since it is the solar year, not the lunar year, that determines the time for harvest and planting. The season seems to drift when you reckon by an uncorrected lunar year. Correcting the lunar calendar is a complicated undertaking. A number of modern day nations like Israel and Saudi Arabia still use a modified lunar calendar. But 6,000 years ago, the Egyptians came up with a better system. Their method was a much simpler way of keeping track of the passage of the day, producing a calendar that stayed in sync with the seasons for many years, instead of using the moon to keep track of the passage of time. The Egyptians used the sun, just as most nations do today. The Egyptian calendar had 12 months, like the lunar one, but each month was 30 days long. Being base, 10 sort of people, their week, the decade, was 10 days long. At the end of the year, there were an extra 5 days, bringing the total up to 365. This calendar was the ancestor of our own calendar. The Egyptian system was adopted by Greece and then by Rome, where it was modified by adding leap years, and then became the standard calendar of the Western world. However, since the Egyptians, the Greeks, and the Romans did not have zero, the Western calendar does not have any zeros, an oversight that would cause problems millennia later. The Egyptians' innovations of the solar calendar was a breakthrough, but they made an even more important mark on history, the innovation of the art of geometry. Even without a zero, the Egyptians had quickly become master of mathematics. They had to, thanks to an angry river. Every year the Nile would overflow its banks and flood the delta. The good news was that the flooding deposited rich alluvial silt all over the field, making the Nile Delta the richest farmland in the ancient world. The bad news was that the river destroyed many of the boundary markers, erasing all of the landmark that told farmers which land was theirs to cultivate. The Egyptians took property rights very seriously. In the Egyptian Book of the Dead, a newly deceased person must swear to the gods that he hasn't cheated his neighbor by stealing his land. It was a sin, punishable by having his herd fed to a horrible beast called the devourer. In Egypt, filching your neighbor's land was considered as grave, an offense as breaking an oath, murdering somebody, or masturbating in a temple. The ancient pharaoh assigned surveyors to assess the damage and reset the boundary marks, and thus geometry was born. These surveyors or rope stretchers, named for their measuring devices and knotting ropes designed to mark right angles, eventually learned to determine the areas of plots of land by dividing them into rectangles and triangles. The Egyptians also learned how to measure the volume of objects like pyramids. Egyptian mathematics was famed throughout the Mediterranean, and it is likely that the early Greek mathematicians, masters of geometry like Thales and Pythagoras, studied in Egypt. Yet, despite the Egyptians' brilliant geometric work, zero was now here to be found with Egypt. This was in part because the Egyptians were of a practical bent. They never progressed beyond measuring volumes and counting days and hours. Mathematics wasn't used for anything impractical except their system of astrology. As a result, their best mathematicians were unable to use the principles of geometry for anything unrelated to real-world problems. They did not take their system of mathematics and turn it into an abstract system of logic. They were also not inclined to put math into their philosophy. The Greeks were different. They embraced the abstract and the philosophical and brought mathematics to its highest point in ancient times. Yet it was not the Greeks who discovered zero. Zero came from east, nor the west. Part 3. The fearsome properties of nothing. It is hard to imagine being afraid of a number, yet zero was inexorably linked with the void, with nothing. There was a primal fear of void and chaos. There was also a fear of zero. Most ancient peoples believed that only emptiness and chaos were present before the universe came to be. The Greeks claimed that at first darkness was the mother of all things, and from darkness sprang chaos. Darkness and chaos then spawned the rest of creation, the Hebrew creation. Max say that the earth was chaotic and void before God showered it with light and formed its features. The Hebrew phrase is tobu vibu. Robert Graves linked these tobu to Tohomot, a primal Semitic dragon that was present at the birth of the universe, and those body became the sky and earth. Bohu was linked to Bohemot, the famed behemoth master of Hebrew legend. The older Hindu tradition tells of a creator who churns the butter of Chavos into the earth, and the Nor myth tells the tale of an open void that gets covered with ice, and from the chaos caused by the mingling of fire and ice was born the primal giant. Emptiness and disorder were the primeval nature state of the cosmos, and there was always a nagging fear that at the end of time, disorder and void would reign once more. Zero represented that void, but the fear of zero went deeper than unease about the void. To the ancient, zero's mathematical properties were inexplicable, as shrouded in mystery as the birth of the universe. This is because zero is different from the other numbers. Unlike the other digits in the Babylonian system, zero never was allowed to stand alone for good reason. A long zero always misbehaves. At the very least, it does not behave the way other numbers do. Add a number to itself and it changes. 1 and 1 is not 1, it is 2. 2 and 2 is 4, but 0 and 0 is 0. This violates the basic principles of numbers called the axiom of Archimedes, which says that if you add something to itself enough times, it will exceed any other number in magnitude. The axiom of Archimedes was phrased in terms of areas. A number was viewed as the difference of two unequal areas. 0 refuses to get bigger. It also refuses to make any other number bigger. Add 2 and 0 and you get 2. It is as if you never bothered to add the numbers in the first place. The same thing happened with subtraction. Take 0 away from 2 and you get 2. 0 has no substance. Yet this substanceless number threatens to undermine the simplest operations in mathematics like multiplication and division. What happens when you multiply by 0? Anything times 0 is 0. So all the tick marks are at 0. Part 4. Nothing comes of nothing. The West reject 0. 0 clashed with one of the central tenets of Western philosophy, a dictum whose roots were in the number philosophy of Pythagoras and whose importance came from the paradoxes of 0. The whole Greek universe rested upon this pillar. There is no void. The Greek universe, created by Pythagoras, Aristotle, and Ptolemy, survived long after the collapse of Greek civilization. In that universe, there is no such thing as nothing. There is no 0. Because of this, the West could not accept 0 for nearly 2 millennia. The consequences were dire. 0's absence would stunt the growth of mathematics, stifle innovation in science, and incidentally make a mess of the calendar. Before they could accept 0, philosophers in the West could have to destroy their universe. Chapter 5. The origin of Greek number philosophy. The Egyptians, who had invented geometry, though little about mathematics, for them it was a tool to reckon the passage of the day and to maintain plots of land. The Greeks had a very different attitude. To them, numbers and philosophy were inseparable, and they took both very seriously. Indeed, the Greeks went overboard when it came to numbers literally. Hippasus of Metapontum stood on the deck preparing to die. Around him stood the members of a cult, a secret brotherhood that he had betrayed. Hippasus had revealed a secret that was deadly to the Greek way of thinking, a secret that threatened to undermine the entire philosophy that the Brotherhood had struggled to build. For revealing that secret, the great Pythagorean himself sentenced Hippasus to death by drowning. The protest their number philosophy, the cult could kill, yet as deadly as the secret that Hippasus revealed was. It was small compared to the danger of zero. The leader of the cult was Pythagoras, an ancient radical. According to most accounts, he was born in 6th century BC on Samos, a Greek island off the coast of Turkey, famed for a temple to Hera and for really good wine. Even by the standard of superstitious ancient Greeks, Pythagoras' beliefs were eccentric. He was firmly convinced that he was the reincarnated soul of Euphorbus, a Trojan hero. This helped convince Pythagoras that all souls, including those of animals, transmigrated to other bodies after death. Because of this, he was a strict vegetarian. Beans, however, were taboo, as they generate flatulence and are like the genitalia. Pythagoras may have been an ancient New Age thinker, but he was a powerful orator, a renowned scholar and a charismatic teacher. He was said to have written the Constitution for Greeks living in Italy. Students flocked to him, and he soon acquired a retinue of followers who wanted to learn from the master. The Pythagoreans lived according to the dicta of their leader. Among other things, they believed that it is best to make love to women in the winter, but not in the summer, that all disease is caused by indigestion, that one should eat raw food and drink only water, and that one must avoid wearing wool. But at the center of their philosophy was the most important tenet of the Pythagoreans, all is number. The Greeks had inherited their numbers from the geometric Egyptians. As a result, in Greek mathematics, there was no significant distinction between shapes and numbers. To the Greek philosopher, mathematicians, they were pretty much the same thing. Even today, we have square numbers and triangular numbers thanks to their influence. In those days, proving a mathematical theorem was often as simple as drawing an elegant picture. The tools of ancient Greek mathematics were in pencil and paper. They were a straight edge and compasses. And to Pythagoras, the connection between shapes and numbers was deep and mystical. Every number shape had a hidden meaning, and the most beautiful number shapes were sacred. The mystical symbol of the Pythagorean cult was naturally a number shape, the pentagram, a 5-pointed star. This symbol figure is a glimpse at the infinite. Nestled within the lines of the star is a pentagon. Connecting the corners of that pentagon with the lines generates a small upside-down 5-pointed star, which is exactly the same as the original star in its proportions. This star, in turn, contains an even number smaller pentagon, which contains a tinier star with its tiny pentagon, and so forth. As interesting as this was, to the Pythagorean, the most important property of the pentagram was not in this self-replication, but was hidden within the lines of the star. They contained a number shape that was the ultimate symbol of the Pythagorean view of the universe, the golden ratio. The importance of the golden ratio comes from a Pythagorean discovery that is now barely remembered. In modern schools, children learn of Pythagoras for his famed theorem. The square of the hypotenuse of a right triangle is equal to the sum of the squares of the other two sides. However, this was in fact ancient news. It was not more than 1000 years before Pythagoras' time. In ancient Greece, Pythagoras was remembered for a different invention, the musical scale. One day, according to legend, Pythagoras was toying with a monochord, a box with a string on it, by moving a sliding bridge up and down the monochord. Pythagoras changed the notes that the device placed. He quickly discovered that strings have a particular yet predictable behavior. When you plug the string without the bridge, you get a clear note, the tone known as the fundamental. Putting the bridge on the monochord so it touches the string changes the notes that are played. When you place the bridge exactly in the middle of the monochord, touching the center of the string, each half of the string plays the same note, a tone exactly one octave higher than the string's fundamental. Shifting the bridge slightly might divide the string so that one side has 3/5 of the string and the other has 2/5. In this case, Pythagoras noticed that the plucking the string segments create two notes that form a perfect fifth, which is said to be the most powerful and evocative musical relationship. Different ratios gave different tones that could soothe or disturb. The discordant tritone, for instance, was dubbed the devil in music and was rejected by medieval musicians. Oddly enough, when Pythagoras put the bridge at a place that did not divide the string into a symbol ratio, the plugged notes did not meld well. The sound was usually dissonant and sometimes even worse. Often the tone bobbled like a drunkard up and down the scale. The Pythagoras playing music was a mathematical act like squares and triangles. Lines were number shapes, so dividing a string into two parts was the same as taking a ratio of two numbers. The harmony of the monochord was the harmony of mathematics and the harmony of the universe. Pythagoras concluded that ratios govern not only music but also all other type of beauty. To the Pythagorean, ratios and proportions controlled musical beauty, physical beauty and mathematical beauty. Understanding nature was as simple as understanding the mathematics of proportions. This philosophy, the interchangeability of music, math and nature, led to the earliest Pythagorean model of the planets. Pythagoras argued that the earth sat at the center of the universe and the sun, moon, planet and stars revolved around the earth, each spinned inside a sphere. The ratio of the size of the spheres were nice and orderly, and as the spheres moved, they made music. The outermost planet, Jupiter and Saturn, moves the fastest and made the highest pitched notes. The innermost one, like the moon, made lower notes. Taken all together, the moving planets made a harmony of the spheres. and the heavens are a beautiful mathematical orchestra. This is what Pythagoras meant when he insisted all is number. Because ratios were the keys to understanding nature, the Pythagoreans and later Greek mathematicians spent much of their energy investigating their properties. Eventually, they categorized proportions into 10 different classes with names like the harmonic mean. One of these means yield the most beautiful number in the world, the golden ratio. Achieving this blissful mean is a matter of dividing a line in a spherical way, divided it into two so that the ratio of the small part of the large part is the same as the ratio of the large part to the whole. In words, it doesn't seem particularly special, but figures imbued with this golden ratio seems to be the most beautiful objects. Even today, artists and architects intuitively know that objects that have this ratio of length to width are the most aesthetically pleasing, and the ratio governs the proportions of many works of art and architecture. Some historians and mathematicians argue that the Parthenon, the majestic Athenian temple, was built so that the golden ratio is visible in every aspect of its construction. Even nature seems to have the golden ratio in its design plans. Compare the ratio of the size of any two succeeding chambers of the Nautilus, or take the ratio of the clockwise grooves to counterclockwise grooves in the pineapple, and you will see that this ratio approach the golden ratio. The pentagram became the most sacred symbol of the Pythagorean brotherhood because the lines of the star are divided in this special way. The pentagram is chock full of the golden ratio, and for Pythagoras, the golden ratio was the king of numbers. The golden ratio was favored by artists and nature alike and seemed to prove the Pythagorean assertion that music, beauty, architecture, nature, and the very constructions of the cosmos were all intertwined and inseparable. To the Pythagorean mind, ratios controlled the universe, and what was true for the Pythagorean soon became true for the entire West. The supernatural link between aesthetics, ratios, and the universe became one of the central and long-lasting tenets of Western civilization. As late as Shakespeare's time, scientists talked about the revolution of orbs of different proportions and discussed the heavenly music that reverberated throughout the cosmos. Zero had no place within the Pythagorean framework. The equivalence of numbers and shapes made the ancient Greeks and the masters of geometry, yet it had a serious drawback. It precluded anyone from treating zero as a number. What shape, after all, would zero be? It is easy to visualize a square with width 2 and height 2, but what is a square with width 0 and height 0? It is hard to imagine something with no width and no height, with no substance at all, being a square. This means that multiplication by 0 didn't make any sense either. Multiplying two numbers was equivalent to taking an area of a rectangle. But what could the area of a rectangle with 0 height or 0 width be? Nowadays, the great unsolved problems in mathematics are stated in terms of conjectures, and the mathematicians are unable to prove. In ancient Greece, however, number shapes inspired a different way of thinking. The famous unsolved problem of the day were geometric, with only a straight edge and compasses. Would you make a square equal in area to a given circle? Would you use those tools to trisect in angle? Geometry, construction and shape were the same thing. 0 was a number that didn't seem to make any geometric sense. So to include it, the Greeks would have had to revamp their entire way of doing mathematics. They chose not to. Even if 0 were a number in the Greek sense, the act of taking a ratio with 0 in it would seem to defy nature. No longer would a proportion be a relationship between two objects. The ratio of 0 to anything, 0 divided by a number, is always 0. The other number is completely consumed by the 0, and the ratio of anything to 0, a number divided by 0, can destroy logic. 0 would punch a hole in the neat Pythagorean order of the universe, and for that reason it could not be tolerated. Indeed, the Pythagorean had tried to sculpt another troublesome mathematical concept, the irrational. This concept was the first challenge to the Pythagorean point of view, and the Brotherhood tried to keep it secret. When the secret leaked out, the cult turned to violence. The concept of the irrational was hidden like a time bomb inside Greek mathematics. Thanks to the number-shaped duality, to the Greeks counting was tantamount to measuring a line. Thus a ratio of two numbers was nothing more than the comparison of two lines of different lengths. However, to make any sort of measurement, you need understand a common yardstick to compare to the size of the line. As an example, imagine a line exactly a foot long. Make a mark, say 5.5 inches from one end, divided the foot into two unequal parts. The Greeks would figure out the ratio by dividing the line into tiny pieces, using, for example, a standard or yardstick half an inch long. One line segment contained 11 of those pieces, the other contained 13. The ratio of the two segments then is 11 to 13. For everything in the universe to be governed by ratios, as the Pythagoreans hoped, everything that made sense in the universe had to relate to a nice, neat proportion. It literally had to be rational. More precisely, these ratios had to be written in the form of A and B, where A and B were nice, neat counting numbers like 1, 2 or 47. Mathematicians are carefully to note that B is not allowed to be 0, for that would be tantamount to division by 0, which we know to be disastrous. Needless to say, the universe is not really that orderly. Some numbers cannot be expressed as a simple ratio of L and B. These irrational numbers were an unavoidable consequence of Greek mathematics. The square is one of the simplest figures of geometry, and it was duly rewarded by Pythagoreans. It had 4 sides corresponding to the 4 elements. It is symbolized the perfection of numbers, but the irrational is nestled within the simplicity of the square. If you draw the diagonal, a line from one corner to the opposite corner, the irrational appears. As a concrete example, imagine a square whose sides are 1 foot long. Draw the diagonal. Ratio-obsessed people like the Greeks naturally looked at the side of the square and the diagonal and asked themselves, What is the ratio of the two lines? The first step again is to create a common yardstick, perhaps a tiny ruler half an inch long. The next step is to use that yardstick to divide each of the two lines into equal segments with a half-inch yardstick. We can divide the foot-long side of the square into 24 segments, each half an inch long. What happens when we measure the diagonal? Using the same yardstick, we see that the diagonal sets almost 34 segments, but it doesn't come out quite evenly. The 34th segment is a wee bit too short. The half-inch ruler juts out a little beyond the corner of the square. We can do better. Let us divide the line into even smaller segment using, say, a ruler 1/6 of an inch long. The side of the square is partitioned into 72 segments, while the diagonal comes out to more than 101 but fewer than 102 segments. Irrationality was dangerous to Pythagoras as it threatened the basis of his ratio universe. To add insult to injury, the Pythagoreans soon discovered that the golden ratio, the ultimate Pythagorean symbol of beauty and rationality, was an irrational number. However, irrational numbers, unlike zero, could not easily be ignored by the Greek. The irrationals occurred and reoccurred in all sorts of geometrical constructions. It would be hard to keep the secret of the irrational hidden from a people who obsessed with geometry and ratios. One day, someone was going to let the secret out. This someone was Hippasus of Metapontum, a mathematician and member of the Pythagorean Brotherhood. The secret of irrationals would cause him great misfortune. The legends are very hazy and contain contradictory stories about the betrayal and ultimate fate of Hippasus. So it was not ignorance that led the Greeks to reject zero, nor was it the restrictive Greek number-shaped system. It was philosophy. Zero conflicted with the fundamental philosophical belief of the West, for contained within zero are two ideas that were poisonous to Western doctrine. Indeed, these concepts would eventually destroy Aristotelian philosophy after its long reign. These dangerous ideas are the void and the infinite. Part 6. The infinite, the void and the West. So naturalists observe, a flea hath smaller fleas that on him prey, and these have smaller yet be bite and so proceed ad infinitum. Jonathan Swift. The infinite and the void had powers that frightened the Greeks. The infinite threatened to make all motion impossible, while the void threatened to smash the nutshell universe into 1,000 flinders. By rejecting zero, the Greek philosophers gave their view of the universe the durability to survive for 2 millennia. Pythagoras' doctrine became the centerpiece of Western philosophy. All the universe was governed by ratios and shapes. The planets moved in heavenly spheres that made music as they turned. But what lay beyond these spheres? Were there more and more spheres, each larger than its neighbor? Or was the outermost sphere the end of the universe? Aristotle and later philosophers would insist that there could not be an infinite number of nested spheres With the adoption of this philosophy, the West had no room for infinity or the infinite. They rejected it outright, for the infinite had already begun to grow at the root of Western thoughts, thanks to Zeno of Elea, a philosopher reckoned by his contemporaries to be the most annoying man in the West. Zeno was born around 490 BC at the beginning of the Persian Wars. A great conflict between East and West. Greece would defeat the Persian. Greek philosophy would never quite defeat Zeno, for Zeno had a paradox, a logical puzzle that seemed intractable to the reasoning of Greek philosophers. It was the most troubling argument in Greece. Zeno had proved the impossible. According to Zeno, nothing in the universe could move. Of course, this is the silly statement. Anyone can refute it by walking across the room. Though everybody knew that Zeno's statement was false, nobody could find a flaw in Zeno's argument. He had come up with a paradox. Zeno's logical puzzle baffled Greek philosophers as well as the philosophers who came after them. Zeno's riddles plagued mathematicians for nearly 2000 years. In his most famous puzzle, the Achilles, Zeno proves that swift Achilles can never catch up with a lumbering tortoise that has a head start. To make things more concrete, let us put some numbers on the problem. Imagine that Achilles runs at a foot a second while the tortoise runs at half that speed. Imagine too that the tortoise starts off a foot ahead of Achilles. Achilles speeds ahead and in a mere second he has caught up to where the tortoise was. But by the time he reaches that point, the tortoise, which is also running, has moved ahead by half a foot. No matter, Achilles is faster, so in half a second he make up the half foot. But again, the tortoise has moved ahead his time by a quarter foot in a flash, a quarter second. Achilles has made up the distance, but the tortoise numbers ahead in that time by an eighth of a foot. Achilles runs and runs, but the tortoise scoots ahead each time. No matter how close Achilles gets to the tortoise, by the time he reaches the point where the tortoise was, the tortoise has moved an eighth of the foot, the 16th of a foot, and a 32nd of a foot, smaller and smaller distance. But Achilles never catches up. The tortoise is always ahead. Everybody knows that in the real world, Achilles would quickly run past the tortoise, but Zeno's argument seemed to prove that Achilles could never catch up. The philosophers of his day were unable to refute the paradox, even though they knew that the conclusion was wrong. They would never find a mistake in Zeno's mathematical proof. The philosopher's main weapon was logic, but logical deduction seemed unless against Zeno's argument. Each step along the way by seemed airtight, and if all the steps are correct, how could the conclusion be wrong? The Greeks were stumped by the problem, but they did find the source of the trouble: infinity. It is the infinite that lies at the heart of Zeno's paradox. Zeno had taken continuous motion and divided it into an infinite number of tiny steps. Because there are an infinite number of steps, the Greek assumed that the race would go on forever and ever. Even though the steps get smaller and smaller, the race would never finish in finite time, or so they thought. The ancients didn't have the equipped to deal with the infinite, but modern mathematicians have learned to handle it. The infinite must be approached very carefully, but it can be mastered. But the half of zero, armed with 2400 years worth of extra mathematics, it is not hard for us to go back and find Zeno's Achilles heel. The Greeks did not have zero, but we do, and it is the key to solving Zeno's puzzle. It is sometimes possible to add infinite terms together to get a finite result. Part 8. The zeroth number. It may seem bizarre to suggest that Dionysius and Bede made a mistake when they forgot to include zero in their calendar. After all, children count 1, 2, 3, not 0, 1, 2, except from the Mayans. Nobody else had a year 0 or started a month with day 0. It seems unnatural. On the other hand, when you count backward, it is second nature. 10, 9, 8, 7. Then 3, 2, 1 left off. The space shuttle always waits for 0 before it blasts into the air. An important event happened at the 0 hour, not the 1 hour. When you drive toward the site where a bomb went off, you are approaching ground zero. If you look carefully enough, you will see that people usually do start counting with 0. When we are dealing with counting numbers 1, 2, 3 and so on, it is easy to rank them in order. 1 is the first counting number, 2 is the second counting number, and 3 is the third. We don't have to worry about mixing up the value of the numbers. Part 9. The gaping void. It is hard to blame the monks for their ignorance. The world of Dionysius, Exos, Beatus, and Bede was dark indeed. Rome had collapsed and Western civilization seemed but the shadow of Rome's past glory. The future seemed more horrid than the past. It is no wonder that in the search for wisdom, medieval scholars didn't look to their peers for ideas. Instead, they turned to the ancient like Aristotle and the Neo-Platonists. As these medieval thinkers imported the philosophy and science of the ancients, they inherited the ancient prejudices, a fear of the infinite and a horror of the void. Medieval scholars branded void as evil and evil as void. Satan was quite literally nothing. Boethius made the argument of following: God is omnipotent. There is nothing God cannot do. But God, the ultimate goodness, cannot do evil. Therefore, evil is nothing. It made perfect sense of the medieval mind. Lurking underneath the veil of medieval philosophy, however, was a conflict. The Aristotelian system was Greek, but the Judeo-Christian story of creation was Semitic, and Semitic didn't have such a fear of the void. The very act of creation was out of a chaotic void, and theologian like Saint Augustine, who lived in the 4th century, tried to explain it away by referring to the state before creation as a nothing something that is empty of form but yet fall short of utter nothingness. The fear of the void was so great that Christian scholars tried to fix the Bible to match Aristotle rather than vice versa. Luckily, not all civilizations were so afraid of zero. Part 10. Nothing ventured. Though the West was afraid of void, the East welcomed it. In Europe, zero was an outcast, but in India and later in Arab lands, it flourished. When we last saw zero, it was simply a placeholder. It was a blank spot in the Babylonian system of numeration. Zero was useful, but was not truly a number on its own. It had no value. It only took its meaning from the digits to its left. The symbol for zero literally meant nothing if it was by itself. In India, all is changed. In the 4th century BC, Alexander the Great marched with his Persian troops from Babylonia to India. It was through this invasion that Indian mathematicians first learned about the Babylonian system of numbers and about zero. When Alexander died in 323 BC, his scabbling generals split his empire into pieces. Rome rose to power in the 2nd century BC and followed by Greece. But Rome's power did not extend as far east as Alexander's had. As a result, remote India was insulted from the rise of Christianity and the fall of Rome in the 4th and 5th centuries AD. India was also insulted from Aristotle's philosophy, though Alexander had been tutored by Aristotle and no doubt introduced India to Aristotelian idea. The Greek philosophy never took hold. Unlike Greece, India never had a fear of infinite or of void. Indeed, it embraced them. The void had an important place in Hindu religion. Hinduism had started off as a polytheistic religion, a set of tales about warrior gods and battles similar in many ways to the Greek mythos. However, over centuries before Alexander arrived, the gods began to merge together, while Hinduism retained its popular rituals and devotion to its pantheon. And its core, Hinduism, became monotheistic and introspective. All the gods became aspects of an all-encompassing God, Brahma. At about the same time that the Greeks were rising in Western world, Hinduism was becoming less like the Western myth. The individual god became less distinct and the religion became more and more mystical. The mysticism was patently Eastern. Like many Eastern religions, Hinduism was steeped in symbolism of duality. Of course, these ideas occasionally came up in Western world, where it was promptly branded as heretical. One example is the Manichaean heresy, which saw the world as being under the influence of equal and opposite source of good and evil, as with the yin and yang of the Far East and Zoroaster's dualism of good and evil in the Near East. Creation and destruction were intermingled in Hinduism. The god Shiva was both creator and destroyer of the world and was depicted with the drum of creation in one hand and a flame of destruction in another. However, Shiva also represented nothingness, one aspect of the deity. Nashkala Shiva was literally the Shiva without parts. He was the ultimate void, the supreme nothing, lifelessness incarnate. But out of the void, the universe was born. as was the infinite. Unlike the Western universe, the Hindu cosmos was infinite in extent. Beyond our own universe were innumerable other universes. At the same time, though, the cosmos never truly abandoned its original emptiness. Nothingness was what the world came from, and to achieve nothingness again became the ultimate goal of mankind. In one story, Death tells a disciples about the soul. Concealed in the heart of all being is the Atman, the spirit, the self, he says, smaller than the smallest atom, greater than the vast spaces. This Atman, which resides in everything, is part of the essence of the universe and is immortal. When a person dies, the Atman is released from the body and soon enter another being. The soul transmigrates and the person is reincarnated. The goal of the Hindu is to free the Atman entirely from the cycle of rebirth, to stop wandering from death to death. The way to achieve the ultimate liberation through lifelessness is to cease paying heed to the illusion of reality. The body, the house of the spirit, is under the power of pleasure and pain, explains a god, and if a man is ruled by his body, then this man can never be free. But once you are able to separate yourself from the whims of the flesh and embrace the silence and nothingness of your soul, you will be liberated. Your Atman will fly from the web of human desire and join the collective consciousness, the infinite soul that suffuses the universe at once, everywhere, and nowhere at the same time. It is infinity and it is nothing. So India, as a society that actually explored the void and the infinite, accepted zero. Part 11. Zero Reincarnation. Indian mathematicians did more than simply accept zero. They transformed it, changing its role from mere placeholder to number. This reincarnation was what gave zero its power. The roots of Indian mathematics are hidden by time. An Indian text written the same year that Rome fell, 476 AD, shows the influence of Greek, Egyptian, and Babylonian mathematics brought by Alexander as he penetrated Indian lands. Like the Egyptians, the Indians had rope stretchers to survey fields and lay out temples. They also had a sophisticated system of astronomy. Like the Greeks, they tried to calculate the distance to the sun. That requires trigonometry. The Indian version was probably derived from the system that the Greek had developed. Sometime around the 5th century AD, Indian mathematicians changed their style of numbering. They moved from the Greek-like system to a Babylonian-style one. An important difference between the new Indian number system and the Babylonian style was that Indian numbers were base 10 instead of base 60. Our numbers evolved from the symbols that the Indians used. By rights, they should be called Indian numerals rather than Arabic ones. Nobody knows when the Indians made the switch to a Babylonian-style place-value number system. The earliest reference to the Hindu numerals comes from the Syrian bishop who wrote in 662 of how the Indians did calculation by means of 9 signs, 9, not 10. 0 was eventually not among them. But it is hard to tell for sure. It is fairly clear that the Hindu numeral were around before the bishop wrote about them. There is evidence that 0 appeared in some variants of Indian symbol by that time, though the bishop hadn't heard about it. In any case, a symbol for 0, the placeholder in the base 10 numbering system, was certainly in use by the 9th century. By then, Indian mathematicians had already made a giant leap. The Indians had borrowed little of Greek geometry. They apparently didn't have a deep interest in the plane figures that the Greeks loved so much. They never worried about whether the diagonal of a square was rational or irrational, nor did they investigate the conic section as Archimedes had. But they did learn how to play with numbers. The Indian system of numbering allowed them to use fancy tricks to add, subtract, multiply, and divide numbers without using an abacus to help them. Thanks to their place number system, they could add and subtract large numbers in roughly the same way we do today. With training, a person could multiply with Indian numeral faster than an abacist could tally. Contrasts between the abacists and the so-called algorists who used Indian numerals were the medieval equivalent of the Kasparov versus Deep Blue chess match. Like Deep Blue, the algorists would win in the end. Though the Indian number system was useful for everyday tasks like addition and multiplication, the true impact of Indian numbers was considerably deeper. Numbers had finally become distinct from geometry. Numbers were used to do more than merely measure objects. Unlike the Greeks, the Indians did not see squares in square numbers or the areas of rectangles when they multiplied two different values. Instead, they saw the interplay of numerals.